Good afternoon, everybody. So it's really great pleasure to be here today, and it's especially exciting to talk after the previous speaker who already introduced quite a number of new materials and how they can be used to bring new functionalities into the regular products. And that's exactly what I would like to talk to you about today: the new materials, but actually more important, new functionalities as well. But let's just, I would like to bring it to a different level, just to say a few words about how do we think about materials in general. And of course, materials are very important for humanity. We even call the ages we live in by the names of the dominant materials: the Bronze Age, the Iron Age. I guess in the context of this conference, we probably should call it not just age, but Metaverse and Bronze Metaverse and Iron Metaverse. The good question is which age, which Metaverse do we live in now? And probably for the first time in history, we actually have a choice, because we can actually call it the digital age, or the silicon age, or the nuclear age. But the message here is that, first of all, I think it's important to make a smart choice. Or maybe even better, we shouldn't make any choice at all. So let me just give you an example, and you will see straight away what do I mean. So here is the periodic table of elements which we have been using in our silicon technology from the very beginning until 1990. So it's silicon, boron, phosphorus for doping, aluminum interconnects, hydrogen, oxygen for passivation. Very simple technology. Even I could probably do it. Then, after 1990, we started to use more and more transistors. The density increased. We needed more conductive interconnects. We added copper. Added copper, we have to add some work-function matching materials, some diffusion barriers, but still relatively simple technology. So these days, we basically use more than half of the periodic table in our silicon technology. So basically something which started as a very simple, very efficient technology, we have to really crank it and make it more and more complex to add complexity to compensate for the functionalities. And actually, if you think how many elements is there in your own body, we actually use more elements, more chemical elements in our silicon chips than in our own body. And that's generally the case. So there are only a few materials which we bet on, and then we increase the complexity of the technology to make it working for us. Like silicon for electronics, construction, it's steel everywhere, aluminum for airspace. Instead, and it actually, sometimes it does work, sometimes it doesn't, but we're actually slaves of those materials. Ideally, you don't want this. You want actually to think freely about the new devices, the new structures you want to construct, but then design materials to fulfill those needs. And that's the concept of the composite materials, which you create for specific applications. But ideally, so those examples do exist, but there are still few and far between. Ideally, you would really want to have those materials, new materials, new structures to be constructed on the atomic level, or at least on the layers level, and then you would be able to create, to design a material which has the top layer is the sensor, then the next few layers would be the solar cell or the power source, then the logic level, and so on and so on and so on. And with the advent of graphene and other two-dimensional materials, we actually have exactly this, because, of course, a part of the fact that we can study the properties of those materials, we can actually combine them together into three-dimensional stack, and we can design materials which we want for our applications, and we can do it with the with the single atom precision, and that's exactly what we do in the lab. So we basically now have a transition from the few dominant material to designer material to the tailored material, those which are specifically designed for applications in transistors, in solar cells, LEDs, and so on and so on and so on. And there are so many materials that we can design them for many different applications. Say, if we're talking about silicon photonics, we can design materials for the photodetector, for the LEDs, for the modulators, and actually even further, if you want quantum telecommunication, then you will have ways how to prepare devices based on the quantum dots. But of course, the problem starts when we really start to design very complex materials like that. And then you really have to challenge yourself, because our computational methods are no good to explain and predict the properties of those complex devices. Quantum dots as well, so we can prepare them, but we don't understand where they're coming from. And that's where the power of the metaverse, of the material metaverses, of the AI comes into play. So we actually can teach and quite successfully those AI algorithms. We have to teach them a bit of the quantum mechanics as well. But if you do it properly, you actually can predict the properties of those materials quite well. So this is just the sort of introduction into a long introduction into the second part of my talk, but it just I wanted you to see that already now what we're doing, we're transitioning from the era when we had a few dominant materials only to the designer materials, to the tailored materials, so we now start to design new materials for every new applications, and we start to use AI for this quite intensively. But now I want you to think, what actually do you want from your materials in the future? So tailored materials, that's great, but say if you would have a completely free hand, what kind of properties, what kind of materials would you like to have? So to answer this question, maybe I just show you this little clip. I guess some of you, so those of you who are my age, do remember this movie. So for those who don't, it's Terminator 2. And the Terminator 2 was shot in 1991. And the plot for the movie is that the robot from 2029 is sent back to 1991 to kill Sarah Connor and her son. But I'm not going to talk about Sarah Connor. The only reason I'm showing it to you is because that's how we back then in '91 were thinking about robots in the future. So they're going to be made from liquid metal, agile, self-healing, changing shape, would be able to change color and so on. So we are in 2022. And I have a little bit of a bad news for you, that, and it's not only about that our programming is no good. So it's actually, we are fundamentally not there to be able to achieve our dreams in 2029. So we still have 7 years to go, but really, it's unless we change something radically, it's not going to work. So, and what is wrong about our technology? So our technology is essentially top-down. So individual components in our systems, they don't have any functionality at all. So you really need to get those cogwheels into a system to make it functional. And that's true about individual transistors, that's true about the robotics. Individual parts, individual components are not functional at all. So that's really true about all our technologies, whichever you take. Now, if you think about biological systems, they actually operate on a completely different principles. There, the functionality is spread across all the different levels. So individual proteins, they're functional in their own rights, cells, even cellular membranes, organs, our body. We don't think that, okay, that protein needs to unfold, get into the cell, fold back, and so on. So we don't think about this. They do it on their own. So the functionality is spread across all the possible levels. And that's what we would like to ask and challenge. Can we produce materials for our technology which are functional in their own rights, not only as part of a system, but functional in their own rights? And that's what we came with the idea of the functional intelligent materials. Functional means that they can be programmed to perform certain response to external stimuli. And intelligent, well, there are many different definitions of intelligence. I'm sure that in this audience you can tell me many of them much more than I can invent, but for us we just want the simplest possible. They can be teach something so that there is a memory inside of our material. So just let me give you an example. I mean, I did work a lot on graphene. So some of the graphene membranes, they're actually quite good for water desalination. So work quite well. So I'm coming from Singapore today. All the water in Singapore is coming from the reverse osmosis membranes. But yet, still, so you can desalinate it, but then still you have to put, you have to ensure the quality of this water. You have to put a sensor there. This sensor just checks the quality, checks the presence of the toxic elements, sends the signal to the computer. Computer analyzes the data, sends the signal to the valve, to the actuator, and then just if there is something funny in the water, it just closes the valve. But imagine that we would try to put all these functions on the membrane itself. So we have those signal molecules and the actuator molecules which change shape, just reconstruct in case there is something funny in the water stream, closes the membrane itself, and then so you basically the membrane, it doesn't only desalinate, but it also acts as a sensor, as a computer, and as an actuator at the same time. And I'll talk about this a bit later. So we need to create those materials which would have this memory function, but just changing the functionality. And we understand what do we actually need from this. I won't go into details, but the answer is that we need the so-called degenerate energy landscape, and it's not really a new idea. That's exactly how our proteins operate. So there are many different energy levels which are quite close to each other, which correspond to different folding and unfolding of those proteins, and that it's those transitions which actually make those proteins functional and being able to have different functionalities in different conditions. The big problem for the design of those materials is that we have to know all those transitions, all those energy levels. So 2 years ago, there was a huge breakthrough in the field of protein folding when AlphaFold solved the ground level of those proteins. Now the next challenge is really to learn and to be able to control all the other levels as well. And unfortunately, what our physical formalism, so the usual stuff which we have, doesn't help, because it only gives you the ground level, so the most basic energy level. So we really have to do a lot of a lot of machine learning and a lot of dynamic machine learning to analyze the dynamic properties, so because of those materials, and we have to do it by using the material robotics lab, because we have to construct a lot of data points to teach that dynamic. And then if you're able to do it, then you should be able to construct new devices, say in electronics, like neuromorphic computers, in energy, in membranes, in bio. Maybe just to give you one more example. 2 days ago, I had my next booster vaccine, and you had to admit it through a jab. And the reason you have to do it because those mRNA vaccines are not stable in your stomach. Low pH would simply kill it. But then, can we design, say, smart capsules which close at the harsh environment and open up only when those drugs are delivered? So again, it's quite an active area of research, but you basically still need those programmable and functional materials. So this is just one example of us studying. So I'm working together with Lee, Chao-Keda, and Beatrice on studying the dynamic proteins, dynamic properties of the folding and unfolding of the polymer chains. And the only way how to do it is through the use of the non-equilibrium dynamics, which we learn through the neural networks. But then it works really fantastically well. We can predict the statistical properties of any folded configuration of those polymer chains. And I thought I would just give you a couple of more examples of the dynamic active and active material. So here is one. It's the composite between bacteria and conductive polymers. And those bacteria, they have this property that they can emit electrons, and those electrons are collected by this conductive chain, and basically we can use it to power external circuit. And the beauty of here is that those bacteria, they help this polymer to polymerize into conductive chain, and the polymer, once polymerized, they help the bacteria to grow. So you basically start with single bacteria and a number of the monomers of the polymer, and then it just grows by itself into a live battery. And at the end, you just throw lactose or sugar into the pot, and you basically literally grow your battery. Here is another example of an active material. So it's the high entropy alloy, and it has, and some of those have this property that they can self-heal. So those are all atoms, and we drill a hole inside. And now we just add a little bit of energy, and because we programmed it in such a way that we stored a lot of energy in the entropy part of this alloy, we just direct this extra energy into the regrowth, and within minutes it just closes itself and completely heals, and you won't see any difference between the heal part and the non-heal part. And you really have to program this functionality on the designer level when you design those materials. So I think I will stop here, but just to conclude that already now we start to use tailored materials more and more in our technology. But really, if you want to think for the future, we have to switch our technology entirely and start thinking about active materials, functional materials, smart materials, and then you can really be able to tackle all those challenging smart applications which we need in the future. Thank you.